Welcome to qnawire.
1 mole of an ideal gas is confined in a cylinder with a movable piston, and we have to calculate the work which is done by gas to expand the volume, while the temperature is held constant. But first we have to answer why delta U, change of the gas internal energy, is 0. So first let's start with the formula which describes the internal energy of a gas at each state. For the initial state, let's label it as U1. The internal energy equals to I over 2 multiplied by nu multiplied by R multiplied by T1. Or yeah, let's leave it T1. So here it's a monatomic gas, therefore I equals to 3. So therefore the initial internal energy equals to 3 over 2 multiplied by nu multiplied by R multiplied by T1. Final internal energy equals to 3 over 2 multiplied by nu multiplied by R multiplied by T2. So as we know, temperature is held constant, therefore T1 equals T2 equals to T0. So therefore delta U, change of the internal energy, equals to U1 minus U2 minus U1, or 3 over 2 nu R multiplied by the difference in temperatures. So both temperatures are the same, therefore this guy equals to 0, and therefore total change of the internal energy is 0, as we had to prove. Sorry. Now let's answer question B. So here we have to calculate the work done by the gas and the amount of heat which was transferred to the gas. So first let's start with the first law of thermodynamics. So Q, the amount of heat which was transferred to the gas, equals to the work performed by the gas plus change of its internal energy. So the second term is 0 as we've shown, therefore it just equals to A. So now we have to calculate A. How would we do it? So as we know, dA equals to PdV, or P as a function of E multiplied by dV. Let's use the Clapeyron-Mendeleev equation. So PV equals to nu RT. Therefore, P equals to nu multiplied by R multiplied by temperature divided by volume. So this is a function which we have to integrate. So let's write down the equation again. dA equals to nu multiplied by R multiplied by T divided by volume multiplied by dV. So now we can integrate the left and the right part. So we basically take an integral of dA, which equals to the integral of nu RT over V multiplied by dV. And if we look at the work done for the gas to change from state 1 to state 2, which happens here, A equals to integral of nu RT over V dV from in the initial volume to the final volume. So it means that we have to calculate this integral. Let's do this. So work done by the gas equals to, we can remove nu R, temperature is constant, therefore we can simplify the integral. So, and we end up with the integral of dV over V from V1 to V2. So this integral equals to natural logarithm of V2 over V1. So, and as we know, nu is 1 mole, as said in the task, therefore work equals to RT multiplied by natural logarithm of V2 over V1. So let's summarize it again. Work done by the gas equals to gas constant multiplied by temperature, in this case it's T0, multiplied by natural logarithm of the final volume over the initial volume. And the amount of the heat transferred to the gas equals to its work. So it is the same. Yeah, here is a solution of this task. I hope I helped you. Thank you very much for submitting.